Hello, this is Junichiro Horikawa, and this is going to be the first tutorial video for me to use geometry nodes from Blender 3.0 to create a simple geometrical animations. And actually, I have just recently start using geometry nodes myself, so I as ongoing learner, I would like to show you my workflow, how I use geometry nodes and how I use to create a simple geometrical animations. When it comes to geometrical animations, there are steps that I always follow in order to create an animation, which is the same as in Houdini, which I will often use to create animations. So with this simple example that I'm showing on the display right now, to show you the workflow that I use to create a project, which works both on Blender or Houdini or other geometry or other softwares. But there are some unique stuff you can do in Blender, which you can only do in Blender, but sometimes there are some stuffs you cannot do in Blender compared to the other software like Houdini. So while I'm doing the step-by-step tutorial, maybe I would like to talk about that as well. So this is the basic workflow that I use to make a geometrical animations. First, I do a research for images or animations that I want to create. This is when you want to collect all the images that you find interesting, and later on you can combine all of those images together to build your own unique image by yourself. Okay. After you have collected the images, after you have done some research on what you want to create, then there comes the next part, next steps to create. Think about the logic, how you could create those images that you have researched or you have found interested. And in order to come up with the logic, you do need to know what's your tool you want to use is capable of. In this case, we are going to use Blender with the geometry nodes, so we need to know the limit, what geometry nodes can do and cannot do at this moment. As a Houdini user or Grasshopper user myself, I do know the limitation what Houdini or Grasshopper can do or cannot do with strength and weaknesses. And I can rather easily create the logic that I would like to create an image for with those tools. But for Blender, you have to think in a different mind because it has its different tool set and it has things that can be done only in Blender and cannot be done in Blender at all with this current version. And in order to understand the limit of this tool, you do need to use this tool again and again and again for different topics that you found interested in. And sometimes it fails, sometimes it succeeds, and throughout those experiments and experiences you will gather those knowledge, what it can do, what it cannot do at this moment. And the same thing can be said for any kind of softwares. You just need to get used to the tool first of all, in order to be able to create things that you imagine. And more you do it, more easily you can build up the logic for the animation or geometries. Now, if you have made the logics, the next thing you want to do is to think about direction, how you're going to visualize the image or the geometry or the animation. Sometimes you want to make a procedural geometry that grows over time. Sometimes you want to make some of the abstract geometry in the animations that loops through time, and so on. That's when you want to decide the direction, how you want to complete the project. Now for myself, when I use Blender, when I practice Blender, I always create some abstract animations which can be looped through time because it's easy to create, it's easy to come up with, and it's just for myself to practice how to use geometry nodes, so that's kind of a reason why I've chosen those directions. It's just a matter of how you want to show it as a final project. After you have decided the logics and direction, then that's when you want to create those logics using the geometry nodes in Blender. Okay, after doing that, the next thing you want to do is to make it look prettier as a rendered image, and that's the final step to visualize the complete project, to complete the project. Now when I create abstract animations on Blender, it always goes like this. First of all, I go to a image searching site like Pinterest, Instagram, Reddit, or any kind of those website that you can search for images and look for an interesting geometries or animations that I found interesting, and collect them together and see what can be done in Blender, or what would be interesting to do in Blender with the geometry nodes. After you have collected all those images and make a collage of what you would like to create, next things you want to do is to create the logics and consider the direction of the image that you want to create using the geometry nodes. That's when you do need to consider the limitation of this tool and what it can do, what it cannot do. But if you are a beginner of this tool, I think you don't have much image what it can do at the first moment. So, well, I think it's a good idea just to dive in to try with the logic that you come up with, even though you don't know whether it's actually possible in geometry nodes or not. And by continuously doing those processes, you'll get used to the tool pretty fast. Okay, and then after you have created the logics, maybe with the animation, with the direction you have chosen, it's time to visualize the geometry that you have created using a powerful shading system in Blender. In this case, I'm going to use the Eevee render. And I do think the last step, the visualization steps, is also really important, because it can easily motivate you when you have finished up with a really pretty image. Even though the geometry itself is pretty simple, if the animations and the visualization, the renderings looks pretty, everything looks pretty and everything looks cool. Although I don't do much visualization when it comes to Houdini, because it's more in Houdini, it's more powerful in terms of creating the logics and applying the direction. But in the case of Blender, when it comes to create the logics and apply the directions, it's a bit more limited, because it has far less number of nodes compared to Houdini. But what's more powerful than Houdini in Blender is this rendering system, the real-time rendering system called Eevee. So that's where I mostly focused on when I use Blender to make a pretty image instead of creating a complex logics. But that's just the way I use Blender compared to the Houdini, but everybody has their own opinion, so I think you should just follow your instinct and do whatever you want to do with this software. Okay, so enough with the theory, let's go to the real practice, how I actually do it. So first is the research. I often go to the Pinterest first and search for something like abstract geometry animations and something like that, or a keyword you want to use to search for a specific topic. And if I search with this, I get those results. And let's say I have chosen this one. This looks interesting. So and this is pretty close to what I'm going to create today as a tutorial. And if we look at this carefully, we do see that the box is graduating, the size of the box is gradually changing with some kind of rule, probably using trigonometry or something. And let's see if we have similar image, something like these. Yeah, we do see some boxes changing its scale based on some logics. Probably there are tons of images like that, and everything has different logics, but at some point you do see some rule in these animations, and that's when you can build up your own logic from those images. Like that. Okay, so in this case what I come up with is to create a bunch of boxes which lies on top of the sphere, and the size of the box is changing based on some attractor field. And when I play the animation, I want to have something that the mass of boxes are moving, the scaled up mass boxes are moving on top of the sphere like a creature. And this is the actual result, and the logic that I have come up here is that there are some basic agents running on top of the sphere, like circularly. And with using the distance between this agent point and all those points on top of the sphere, based on those distance, I can change the scale of those boxes. So if the box is close to the agent point, then the box becomes bigger. If it's far, then it becomes smaller. So, and agent is moving regularly within the loop. You always get these loop animation box changing its size. And at the same time, box is also rotated kind of randomly, but also see some regularity here. In this case, I'm using the function called Noes to create a random but also a bit regularized value. Okay, in order to rotate this kind of a organic like rotation. And the direction here is to create a loop animation which can always come back to the same position when you go from a first frame to the last frame, goes back to the first frame and becomes loopable like this. So it always comes back to the same positions and same rotation and continuously going back and forth. Now finally, I'm using Eevee render to visualize the image that I've created, and in this case it is pretty easy because you can see that there's only like a few nodes to set up and a little bit of lightings as well. Now that we have some image what to create, let's start creating these image or animations using geometry nodes. So when you open up the geometry, when Blender, in this case 3.0, you have these box and you have this cube, camera and light. Now when you want to use the geometry nodes, first you go to this geometry node sections by clicking here, and it will open up 3 windows. On the left top side you have a spreadsheet where you can gather all those informations for each point, for vertices, edges, faces and so on. And on the right top corner you have the viewport where you can navigate the 3D geometry that you're creating. And on the bottom, this is the main part for the geometry nodes where you can construct the node network in order to create a procedural geometry system. Okay, so in order to start creating the geometry, you first need to create the geometry nodes on any given any selected geometries. Like in this case, you can create a geometry nodes on top of this cube. So please select the cube first, and then click this new button on the bottom window. Then it will create a geometry nose on top of this cube, and you'll see that the little blue icon has been created to this cube. Okay, this indicates that it has a geometry nose modifier. Okay, now you can define the name first. Let's say I'm going to say sphere box dancer or something. After you do that, let's see what you have inside this geometry node. So you have this group input, which gives you the geometry output, which is this cube itself, and the geometry output is the target, the goal of this node. So when the geometry network has been connected from this group input to group output, you are just passing this cube from input to output. So when you disconnect this network by dragging from the output to nowhere, you'll see that the geometry has been disappeared. That is because you haven't connected anything to the group output. So anything that has been connected to the group output will shown up in the viewport. So let's try to create the sphere first, since what we're going to create is the boxes on top of the sphere. And in order to search for the node on Blender, what you can do is to type Shift A, which will give you a search box for all the nodes available on Blender, geometry nodes. And you can go through all the nodes, which isn't that much right now. But the things that I want to have is the sphere, so probably that's under mesh primitive, and we can use this icosphere. So let's bring that up, click, and place it on the canvas. And this is the node for the icosphere. And in order to show this up inside the viewport, you can just connect this mesh output to this group output geometry. And there you go, you see the geometry as an icosphere. Now this is a bit too low res in terms of the sphere, so let's try to make this more high res. And you can do that by increasing the subdivisions. If you click this arrow, you can see that the resolution is increasing by increasing this number. Now you can also increase this number with a input right here by inputting the number of your choice. You can directly type the number here, but you can also do that from outside as well. When you want to do that, you search for a value node called integer. Search for an input, and then under an input there's one called integer, which create an integer value, and there you can also type in the value, and you can connect this to this subdivision as a network, and then you can control these subdivision from outside. Now you can also do that from as a parameter of this cube geometry that you have selected. Right now there are no parameters available in this cube, but you can add your own parameters to this cube when you click this icon. When you click this gear icon, you'll see a bunch of parameters under here. Right now there are no parameters, but when you connect this empty output right here to this subdivision, you start to see this new parameters appear under this geometry nodes modifier. And by changing this value, you can see that this subdivision is also changing, which means that this parameter value has been linked to this subdivision's output that has been just created and then connected to the network like these. So this is how you can create your own parameter for this geometry for this geometry nose. You can also rename this if you don't like the name subdivisions. First of all, you can go to this small arrow button and open up this tab, and under a group tab there's one that you have just created, and by clicking this you can change the name. So let's say I want to make this named as resolution, and you can also set the minimum and maximum amount of value for the subdivision. Let's say I want to make the maximum 5 and minimum 2, like this. And by doing this, you can limit the number of parameters, the value for the parameters, which in this case the maximum will be 5, the minimum will be 2, like this, and the name has been changed to resolution. Now next thing what we would like to do here is to place boxes on top of each vertices on top of the sphere. So each this sphere has a bunch of vertices, as you can see, like this. And if you look at the left top corner, the spreadsheet, it shows up all those position value for the vertices. In this case, we have 162 vertices for this sphere, and the value here, the information on this spreadsheet is always coming from this group output. Okay, so any geometry that has been connected to the group output geometry is going to be shown up here on the spreadsheet. There are also a visualize node to visualize the geometry before connecting to the group output, but without using it, it's always the case that the geometry that has been connected to group output will be shown here. Now we can see that we have 162 points, so vertices. So what we expect to have is 162 boxes on top of each vertex. 162 boxes in total placed on each vertices. Okay, so to do that, we're going to use the technique called instancing in Blender, and I think we do use a lot of instancing in Blender. Instancing is to create a template of a geometry and then copy that geometry several times, multiple times on different positions. And for those instances, what you can do is to change the position, change the scale, and change the rotation. You cannot modify each instance vertex position and so on. You can just change the center, the middle, the core position of those instance template object. That there are some limitation with the instancing, but what's good about it is that it's pretty fast to visualize, and it's really good for real-time animation. Okay, so let's try to do that. In order to create an instances on each vertices, what we're going to use is the node called, let's search for the nodes by Shift A, and if you want to search, you can click this search or type S, and then we'll search for instances, and there are nodes called instance on points. We're going to use this one. Bring this somewhere on the canvas, and what you want to first set is the point position where you want to set the instance. In this case, we would like to use the points on this icosphere, so we're going to just directly connect this to this points. Okay, then connect the instances to the group output instead. Now we haven't set any template geometry yet as an instance, so we don't see anything yet. In order to set the instance, we need to apply some geometry into this instance input. So let's bring up the cube by searching the cube and connect this mesh to this instance. As do it, you see a bunch of boxes has been copied as an instance to each vertices. Now the size of the box currently is a bit too large, so let's make it a bit smaller by changing this size parameter. Let's say if I set 0.1, 0.1 and 0.1, now you start to see that the box has correctly been positioned on top of each vertices. Now let's make the default value for the size to be a little bit bigger, like 0.5, 5, maybe a bit smaller, maybe 0.4, 0.4 and 0.4. Okay, so let's say that this is the default size for each boxes. And what we want to do next is to rescale these boxes based on some external informations. In this case, we're going to create some agents orbiting around this sphere, and based on this distance between this orbit point and each of the boxes, we would like to set the scale based on this distance. So if the distance is close, then the box size becomes bigger, and if the distance is far, then we'll make the box scale smaller. Okay, first of all, in order to change the scale, for instance, there are just the nodes for that. So let's try to use that first. I'm gonna tidy these things up a little bit. Okay, so let's bring up the new node called scale instances. Scale instances can be used to control the scaling for each instance available. So first things we want to do is to connect the scale instance in between this instance on points and geometry group output. We can just drag and drop, and you'll see that the network has been highlighted to white, and once you see that, just release your mouse and the network will be connected like this. And there are parameters called scale here, which you can use to scale each instances. Now you can see that all the instances changing at the same time with the same value, but actually you can control each instance getting a different value using a something called field. Now the concept of field is a bit hard to understand. I think it's a unique thing in Blender geometry nodes, which isn't available in Houdini or Grasshopper or any other softwares that I know of. Maybe there are some, but the concept of field is a bit special, which is in my understanding, it's a bunch of values available for geometries. In this case, we have these instances. If we look at the spreadsheet, we have 162 instances right here, and each instance has its own unique value. In this case, we have positions, rotation, and scale, like this. And in meaning that we can access to those informations as a list. Okay, in this case, what we want to get is this position information of these instances. Now, in order to get the position information of these instances, you can use the node called a position. Now, things about this position, the unique thing about this position is that it doesn't have any input, like what kind of position you want to get. It just gives you a position. And the first time I saw this, I didn't really understand what this position comes from. but that I realized that it only works when it interact with other nodes. So meaning that when this position interact with this scale instance, it gets the position of these instances, okay, which is this instance which is scaling with this one. But if you have another instance node somewhere, maybe if you have copied these whole stuff, and let's say the subdivision is 2, and connect with this scale instance. Now if you use this position for these network, then the position will get the information for this scale instance. In this case, there will be much less instance numbers. For example, if you want to connect this position to here, in this case, if we connect this position to here, based on the position value, the scale changes like this. So this is what it is being called field in Blender. I think it will take a little bit of time to understand what really is for this one. But if you continue using this tool, I think you'll get used to this. What I always remember is that when the node doesn't have any input to gather information, for example like these positions, then it always gather from the connected network. So in this case, the position has been connected to this scale instance, meaning it is getting the position of these instances. So it's going backward, getting the information backward. That's a bit special like concept, I think, and a bit hard to understand concept. I assume that this idea of field is making the calculation faster by probably using the Perl computation or something in the background. Okay, that's what I imagine. Okay, so that's how it works. So we don't really want to connect this position directly to the scale, but what we want to do is to calculate the distance between this box position, each box position, and a single point which orbits around the sphere. So what we need to do next is to create a orbit point which moves around this sphere, okay, in order to calculate the distance between these instance positions. Okay, so let's do that next. First of all, let me go back to the scale instance and set this back to 1, 1, and 1. Alright, and maybe I could also increase the radius of this sphere, or maybe I can make another parameter in order to control this radius. So let's create the parameter radius. I'm gonna make it all lowercase, and the minimum 0, infinite, the maximum probably 10. Let's increase the radius a little bit, like 3.5 now. Okay, so let's try to create an agent point which rotates around this big sphere. So in order to do that, what I'm gonna do is to create a position information as a vector value. Vector value is a XYZ value, which can be used to determine the direction or position. In this case, we're going to use it as a position. Okay, and we also want to rotate the points around the sphere. So the first thing I would like to do is to create the points somewhere around here. Okay, or outside the sphere, inside the sphere, doesn't really matter. Let's just create the points on the x-axis, the positive point position. Then the next thing what we're going to do is to rotate this point using the z-axis, either clockwise or counterclockwise. Okay, so let's create the first point position somewhere around here. And in order to create the vector value as a position, you can use the node called combine x, y, z, which will create a 3 float value as a vector x, y, z. And in this case, we only want to control the x value to get the position, set the position somewhere around here. So let's set this x value to any value you want, maybe like 4, or could be the same as this radius of the sphere, so that it will attach on top of this. It will come on top of, directly on top of the sphere, because the distance from the center to this edge is the same as this radius. So we're going to connect the same radius value to x. Okay. Now, since this is the vector value and this doesn't have any geometry information, we cannot visualize this directly. We cannot really connect to see where the point position is. So if you want to test out where the point position is currently, we can create some random geometry, like another icosphere, make it really small, like 0.1, and use a node like transform node to move this icosphere with this translation option using this point position information that you have created, and I'll put the geometry. Now you can see that where the point position has been created. Now that's good. Now next thing you want to do is to rotate this point clockwise or counterclockwise using this point as and z-axis. So to do that, you can use this same transform if you're dealing with the geometry, but in this case you don't really want to rotate the geometry itself, but you want to rotate the vector value, which doesn't really have any geometry information. That is because you want to compare with this position later, and you can only compare vectors with other vectors. So you do need to deal with vectors instead of the geometries when you do the comparison, like calculate the distance and so on. So what we want to do is to rotate this vector value. In order to do that, there are just a node for that is called vector rotate. Using this node, you can rotate the vector value using a specific axis and the center point position. Connect this like this. Now it says the default center value is 0, 0, 0, which is right here, so that's fine, I think. And the axis is 0, 0, 1, meaning the z value is equal to 1, so which means that is the z-axis, which we want to use it for a rotation. So that's also good. So everything is good for the center and axis. We just need to change this angle value in order to rotate the vector. And after we have rotated the vector, this rotated vector is going to be used as a translation of this icosphere to visualize it. So let's see if everything is going to be updated, and you can see that when we control this angle value, the angle of the sphere is also changing and it's rotating. So we have just created the orbit sphere available. Now we haven't created the animation yet, we're just moving this value manually by dragging left to right. So in order to make it as an animation, we need to bring up some animation related value, frame related value. Okay, so that's the next step. Now, if we go back to the layout view, you can see that there's a timeline on the underneath, and if you play this, see that the value is changing right here. Now this is called, these are the frame value, and what we want to do is to bring this frame value to the geometry nose in order to create an animation. So every time the frame changes, the value will be transferred into geometry nose and can be used together with other parameters or other values to create an animation. In Blender 3.0, we don't officially have a frame value available inside the geometry nose, but in 3.1 it is said that the frame node frame information can be retrieved from a official node, the new node. So we could come back to use that when the 3.1 is going to be officially released. But for now, in order to use the time base value or frame base value, we need to get an information using a driver, the one that's called driver, which can be accessed from these parameters under the modifier. So first thing to do is to create an input to create a parameter right here. Now last time in order to create an input parameter, we have drag and drop this network to connect to any input to create the parameters, but we can also go to the tab here under a group, and under an inputs you can click this plus button to create your own parameter by yourself as well. So in this case, let's name this frame, and we can set this to float or integer. Since the frame value is the integer value, maybe we can call this as integer. Okay, now going back to this modifier parameters, we see that there's a new value has been created right here, and what we want to do here is to set the driver so that we can get the frame value, the global frame value, which changes through time. And in order to use that, we type a hash frame by doing and enter. By doing it, you can get the current frame value like this. If you play it by typing space key, you can see that the value is changing while it's playing. Okay, so that will be the frame value you get, and which changes in real time and coming from this frame input. Okay, now that I have this frame value changing from time to time, let's convert this to an angle value and connect it to here. Now it seems like the frame can be directly connected to here, but it is not recommended. That is because when you connect the value or number values to an angle, it will be converted into the radians. I mean, it's not going to be used as a degrees, but it's going to be used as the radians value. Radian is the value or the metrics can be used to specify the angle, which often shows as pi, 3.14, and so on. And when it says pi 3.14, it means in degrees it's 180 degrees. And if you want to have an angle of 360 degrees, which is one rotation value, one loop rotation value, it's 2 pi, 2 multiplied by pi, 3.28, 6.28. Okay. So the first thing you need to do is to convert this frame into the radians in order to use it as an angle here. So in order to do that, there is a node called math, and under this option, under this drop-down menu, there are a bunch of mathematical related operators. What we're going to use here is use this one called 2 radians, which will convert the degree value into radians. And what we want to do is to connect this frame to this input to convert this into radians, then connect this to the angle. Okay, so by doing it, and let's also make this icosphere size a little bit bigger so that we can see the change a bit more. Now, right now, the sphere is placed right here, and if I press space key, start to animate. In this case, one frame meaning 1 degrees, and then convert it into radians, and it jumps from somewhere around here to 0. That is because we only have, I think, 250 frames. But in order to rotate fully, we do need to have 360 degrees. So let's change the end value to 360 so that we can create the loop animation. Okay, so let's see what happens. I play it, and let's see if it goes till the end and can be rotated as a loop animation. And there you go. Now it loops from 0 to 360 degrees and go back to 0 again. If you want to make the rotation faster, you can apply some multiplier to this angle value. When you multiply this by 2, the rotation speed becomes 2 times faster. It can be applied, the multiplier can be applied before the radians or after the radians. Let's do it after the radians to see what happens. So I'm going to use another math node. In this case, we're going to use multiply operator, connect this, and multiply by 2. And then the rotation speeds become 2 times faster. Now I think I like this speed, so let's go with this one. Now that we have actually created the rotating vector value, it's time to actually calculate the distance between the instances and this rotating agent. So let's do this. So what we want to compare is the instance position, the distance between the instance position, which is this one, and this one, the vector value that is being rotated using the time frame. Okay, so in order to calculate the distance between two vectors, what we can use is another math node, but in this case we're going to use the one called vector math. And under vector math drop down menu, there are a bunch of different operators compared to the normal math node, and there are some vector specific operators like distance, length, and cross product, dot product, which you're going to use a lot when you do the vector operations, but in this case we're going to use this distance. Okay, so distance is straightforward. You can just calculate the distance between two vectors. Now you'll get a single float value for each instances, which is the distance between the agent and each instance points. So if you have 162 instances, which that means you have 162 different distance value for each instance. Okay, and that is called as field, I think. And using those information, you can use it together with this instance as a field value. And what you want to use it for is this scale value. So let's try using this with the scale. if you directly connect with this scale, then the single value will be converted into a vector value and all x, y, z will be applied with the same value. And let's see what happens by visualizing these instances. Now, you can see that something is going on, but the scale value is a bit too big. We cannot really actually see what's going on here. So let's try to reduce the scale size by remapping this distance to a reusable value, somewhere more lower value. That's when it comes to a method called remapping. I think the concept of remapping value is available in any kind of softwares, including Blender, Houdini, Grasshopper, any kind of software, especially in this kind of node-based programming tools, and which is used to remap one number from a domain or source domain into a target domain, and it is often be used to change the value domains or target range. Now in Blender, in different software has different names in terms of this remapping value. In Blender, it is called as map range. So we're going to use this map range to convert this distance value from one range to another range. Okay, so let's try to use this. So what we're going to use is to connect this between the distance and the scale instance. And first thing we need to define is the source minimum source range, which is the minimum value for the source and the maximum value for the source. Then we also have to apply set the value for the target value to convert, whether you want to make the value, if you want to make the value in between 0 to 1 as a result, then you write like this. But if you want to have the value in between 1 to 2, then you type 1 to 2 like that. So first thing we need to define is what's the minimum of this distance and what's the maximum of this distance. Now in this case, the minimum value is obviously 0, I think, because it is touching to the sphere. So if it's touching and the box is right at the position, then the distance is equal to 0. So we can just say the minimum is equal to 0. Now for the maximum, it will varies. It varies based on this input value. You can increase the value more, increase or make the values really low. So it probably is a good idea to make this as a parameter so that you can change later throughout this input under the geometry nodes modifier. So let's bring up another group input, because the group input right here is a bit too far, but you can add as much group input as you want. It just is a same thing. It just are the same things. It has all the same inputs and output the same value. So it's not a problem having multiple number of group input. Now we don't really have this maximum value yet, so let's just connect the empty output to this max. Now let's rename this to, let's say, search distance, and the default value maybe 10, and the minimum is equal to 0, maximum could be 100 probably. Okay, and let's set this value inside a modifier to be starting with 4 or something. And let's also set the minimum and maximum of the target to be maybe 0.1 to 1. Maybe it's a bit hard to see what's going on here. Or maybe if the point is close to the agent, maybe we do want to have more scaled up values. So maybe if it's close to 0, then that's this target. So let's make this bigger value, like 3. Now looks interesting. Now 2. And then if it's far away from the agent, then let's make this 0.1 or maybe 0.2. Now that starts to have something that I want. And if I increase the search radius, gradually you can increase the size, the scale of the box based on the distance. And if I play it, the box is already starting to create a scaling animation based on the point position of the agents and the instances. Okay. Looks good. Maybe it is also a good idea to make these value parameterized as well. So let's make that. I'm gonna make name this as a minimum scale, starting from 0 to, I don't know, 10. And connect another one to here, and this will be a maximum scale. So max scale from 0 to 10 probably. Now you can control these stuff inside the modifier manually. Like that. Okay, looks good. If we increase the subdivisions, you have more boxes available. Maybe we can test out with 3. Alright, looking good. Now I can see that the box size is changing horizontally, which is close to this X and Y axis right here. But let's say if I want to change the box's scale more on the upper part of the sphere or lower part of the sphere. In order to do that, we need to change the height of this agent moving, orbiting around the sphere. So to do that, we can go back to where we are defining the position of the orbit sphere, which is around here, using the combine XYZ to create the point position, the initial point position of the agent sphere rotating around. And when we change this Z value, we can actually change where the initial agent point position is set. So if we increase this value, Z value, then the point will be set somewhere around here on upper corner of this sphere. If we make this negative value, then the sphere comes underneath the sphere, and the boxes at the lower part will become larger in this case, based on the distance. So I think it is also a good idea to make this value parameterized as well. So let's create another parameter to control the C value. And let's name this agent height. In this case, we do want to have a negative value. So let's say the minimum is -5 and the positive is +5. Maybe -10 to 10 might be a good number. Okay, now we can control the weight of the box scaling based on the height. Alright, looking good. Let's set this to 2.5 for now. Now we're almost done, but there are some things that I'm kind of missing. That is the rotation of these boxes itself. Now currently the box stays as they are right now, and it's not doing anything. It's just changing the scale value like this. But it is still interesting, but I do want to have more interaction with the agents. I do want to make these boxes also rotated using the center of its instances. So in order to do that, we can use another node to rotate its instances, which is called as rotate instance. Now we can do it after the scale instance or before the scale instance. Doesn't really matter in this case, but it's called as rotate instance. Let's say we want to do it before scaling. Okay, and let's bring this up a little bit. And in order to rotate, since this works on the local space by clicking this one, meaning it is using the center of this instance as the rotation axis point position. Okay, and then use this X, Y, or Z to do the rotation using the so-called Euler angles. Using X, Y, Z with the degrees, which that is called as Euler angles. Okay. So what we want to do is to control these X, Y, and Z value using some kind of random value, but bit more wavy organic value, which we're gonna use as a noise value. Okay, so that's what we would like to do, and I would like to change this random value based on the time, so that it will become more wavy, like organic, like rotation available. And we also want to make it loopable so that you don't see any glitches between the frame 0 to frame 360. Alright, so that's the goal here. So let's try to do this. I am going to create another group input to make it a bit tidier, and we're going to access this frame value again together with one called noise texture in order to create the noise value, which is a type of random value but based on some input vector value or float value in order to create a noise random value. So meaning if the input value is close enough, then you get the close value. If the input value is far, like if you input the value 0 and if you input the value 10 at the same time, you get really far value in between those two values as an output. But if you input 0 on one side and if you input 1 on the other side, where the distance between those values is close, you get really close random value like 0.1 and 0.2. Let's just try to see it in the actual node, how it works. So search for noise texture, and there is an input called input where it says vector. This is where you input the point position value in order to calculate a specific noise value for that specific position. Okay. Now in this case we want to use the point position of these instances again, so we are going to use this position. Now at this moment we are not sure where this position comes from, but by interacting, by connecting this noise texture somehow to this rotation instance later, this position will become a part of this instance. So like I said, that's how the field works. It's a bit hard to understand concept, but you'll get used to it. So let's assume that we are getting the instance position out of this node. So let's connect this to vector first. Okay. Now as a result, you get a value in single value as a float, or a color value, which is X, Y, Z, and or RGB and alpha, so you get 4 value. Now in this case we only need 3 values for the rotation, so we can just use this color value converted into a vector. Okay, so let's do that by using a vector math value and connect this into one of the vector value. Now in this case we would like to make this noise value to be the range in between let's say -1 to +1, but currently the default value, the default range for the noise is in between 0 to 1 for a single flow value, or and a color value it always is in between 0 to 1 for all the components X, RGB, alpha. So first thing we want to do is to make these range between -1 to +1. In order to do that, we first subtract this color value by 0.5 for X, Y, and Z. By doing it, you'll get the range in between -0.5 to +0.5 for all X, Y, and Z. Okay. Now after doing that, I'm gonna duplicate this node by Shift D, and then change the operator to multiply. Then connect the vector and then multiply each component with 2. As a result, you'll get a value in between -1 to +1 for all X, Y, and Z. Okay. Now we are ready to combine this or convert this into an angle. In order to do that, we do need to create a radiance value for this rotation. Every rotation related value has to be created with the radians. Even though it looks like it's shown in degrees in this parameter, when you are inputting this value inside to this rotation, you do need to input in radians. That's a bit confusing, but every time you use an angle related value, it always has to be radians. So you just need to remember that. Okay, so in order to convert this value, which is in between -1 to 1, into an angle, what we can do is to multiply this vector value by a maximum angle value. Like let's say we want to create the angle between -180 degrees to +180 degrees. You just need to multiply this by 180. Then as a result you get a value in between -180 to +180. So let's do that by having another multiply, and then let's create a value called 180. Now connect this to here, but before connecting to this vector, as I said, we do need to convert this into the radians. So let's have another math node, convert it into radians, and finally multiply using the vector math. Now, as I said, if you connect the float value into the vector input, all the X, Y, Z will be using this single float value. So all the X, Y, Z will be multiplied by this 180 degree value converted into radians. Now we are ready to use this as a rotation value. Let's connect this to right here. As a result, something has happened to the box. The box is rotating based on its position using the noise value, and you can see that it's randomly rotating the box. Now it looks a bit too randomish, so in order to make this a bit more smoother based on the position or the distance between the neighborhood, you can tweak this scale value to control the smoothness of the noise. If you make it lower, you get more smoother value. let's say it's around 0.4, you get more smoother value. Maybe 0.1 might be more smoother. You can see that the rotation becomes more natural or more organically wavy. If you make it more lower, like 0.05, you get more close. Each angle in the neighborhood becomes more closer. But if you set some high value, it gets more randomish. So this itself is pretty important when you use the scale, the noise texture value. Let's say, for myself, I'm gonna just set it to 0.1 as a default value. If you want, you can make it as another parameter by connecting this right here. But I don't want to make this too much parameters because it's gonna be a bit busy. So I'm gonna keep this value as 0.1 for now. Okay, and you can also control the roughness to make more smoothness. I'm gonna set this to 0.5 as a default value. All the other things, try to see what we'll get. Distortion will create a distorted noise value. That's also an interesting thing. Now, another thing you might want to do is to change the rotation value throughout the time. Now, it's not really changing. The rotation is not really changing throughout the time. So, in order to do that, we do need to use this frame somehow. Okay. So, let's try to do this. First of all, I'm going to convert this frame into a radians so that I can use it as an angle. Okay, like this. Now, the important thing here is that we do want to create the loop animation. So even though we do want to rotate, even though we want to create the rotation animation from the first frame to the end frame, we do need to from end frame to the first frame, we do need to link or continuously go back to the same rotation value. So that's the key concept here in order to create the loop animation. Now keep that in mind, and first thing we need to think about is how we can use this frame-based value in order to change the rotation. Okay, we have to think about what kind of parameters can be changed in order to change the rotation value. And if we go back from rotation to the input, it is based on this position. So by changing this position, we can assume that the rotation value is going to be changed. So let's try to modify this position a little bit by having another vector math in between the position and the noise texture. And let's try testing out by using that add operation and add some values here. See how the rotation changes. You can see that if I change the X value, I do see the rotation is changing, same as Y or Z. Okay, so we have got the information that by changing those position value, or by modifying the position value, we can change the rotation itself. So meaning if we, let's say if we apply this rotation or radians value coming from the frame to the vector, we can actually rotate the value through using the time value. Okay, that's good. But the problem is, as you can see, there are some glitch from the last frame to the first frame if we do something like that. So let's go from somewhere close to the 360 degrees, and you see that the rotation is jumping from 360 degrees to 0 degrees. So that's where I want to fix to make a smooth connection between the end frame to the first frame. So how do we do that? We, in this case, what we need to do is to make the position come back to the same position when it goes from 360 frames to the 0 frame. Now, if you just add this time-based value to the position is changing linearly from frame 0 to frame 360 degree, frame 360. So when you goes from 360 frame to 0 frame, the position jumps a lot, meaning you have totally different noise value from end to first. So what we need to do is to make this position come back to the same position, meaning the position on the frame 0 and the position on the 360 should be the same in order to create the loop animation. Now how do we do that? In order to do that, there are some ideas, but the easiest idea I could think of is to use a trigonometry to create a bouncing value, go back and forth. Now, if you heard about trigonometry, it's a value to calculate the triangular edges, edge distances or lengths using an angle, and it can also be used to calculate the position on top of the circle, okay, by using the cosine and sine at the same time. Using the cosine value for the x value and using the sine value for the y value, you'll be able to calculate, or you'll be able to estimate the point position on top of the circle. And as you can see, the circle position can be determined, or the circle position is going from 0 angle to 360 angle and come back to the same positions. So using this concept of trigonometry to use the circular positions, you can actually create a vector value goes from one position, go to another positions using the rotation, and then come back to the same position. And by adding those this rotating information, you can make this position come back to the same position on the last frame. Alright, so let's try to create that. So in order to use a trigonometry, use the math node. Again, there is one called cosine and one called sine. And cosine and sine are used with their angle value. Connect this radians to each of this value to calculate the cosine and sine value. And as I said, in order to get the circle, the point on the circle positions, the cosine will become the x value on top of the circle, and sine will become the y value on top of the circle. So combine those two values in a vector value, x and y, to create a point position on top of the circle, which is actually the same as this vector rotate. This is another way to create the point on top of the circle, but you can also do exactly the same thing like this using trigonometry, which is a technique you use a lot if you are creating like this kind of geometry animations. Right? And if you directly use cosine and sine, then the radius of the circle is always equal to 1. So if you want to increase the radius, you do have to multiply this by some multiplier value. So let's add another vector math to multiply with some radius of your choice. I'm gonna say 10 for now. Maybe That might go too fast, but let's see. The value here indicates the speed of the rotation and also the radius of the circle. Okay, and now that I have created this circular value, circular position value, which goes from 1 point and goes clockwise, I think, well, counterclockwise, I'm not sure, then goes back to the same position in the last frame. So let's connect this to here and see what happens. If I play it, see that the box is rotating nicely. And let's go back to the layout and go close to 360 degrees and see the animation has smoothly connected from 360 degrees, 360 frame to 0 frame, like this. All right, looks good. So that's everything that I wanted to do for the geometries, and now that we have a geometry that I want to visualize, it's time to actually render it using Eevee. Now before doing that, let's organize these a little bit so that we can see what's going on in each place. So I'm going to create a node called frame, which can gather all sorts of nodes and select the frame as well as all the nodes using the shift and type Control P to insert those nodes inside the frame. Okay, now let's do the same for all this one. Create another frame, Control P. If you want to remove the node from the frame, you can click one of the node and type Alt P, or in Macintosh it's Option P. Okay. Or if you want to go make this back into the frame, you can also drag this inside the frame and then it will automatically attach to the frame. Alright. Let's tie these things up a little bit more. So this is the instancing part. We could bring these here. This is instance related stuff. Let's create another frame. Oops. Control P. Okay, so and this is the agent part, and we no longer need these transforms, so I'm gonna delete that by function delete or delete key. And let's create another frame. Oops. Frame, Control P. We can actually create a comment on top of this frame by clicking it, and there's, if you click this node tab, there's one called label, so we can say agent instance distance. And let's make the size a little bit bigger, like that. Okay, and this is instancing, and this is, what was it? This is more of a rotation from the noise. So rotation from noise, and this is a noise value. Okay, and we have an output and an input. Okay, that's good. Let me save this so that I don't lose the process. Right. Now it's time to set the material for this sphere next, and this is going to be the last step, and we're going to use Eevee render to render this geometry in real time with a bit of shadings. Okay, so first thing to do is to set the material to this geometry. So we can do that by adding another node called set material. And currently there are one default material being created for this node, which original cube had, and we can choose that by going to clicking this drop down menu, and there is one called material. Let's select that, and in order to in order to edit this material, you need to go to this material tab while clicking this cube geometry, and there you see this material name called material. Let's rename this to box. Okay, and you can see that the name has been changed here as well. Let's try to change the color to see if you can see the changes. Now it's not really changing anything. That is because you are not viewing in the shading mode. So let's change to the Eevee shading mode or Eevee rendering mode by going to the right top corner of this viewport and click this one, the viewport shading. And by doing that, you are looking at the Eevee render viewport. Maybe some people are showing it as cycles, which is a different render, which is a bit slower but can create more prettier image. But it in my case, I'm just going to use the Eevee because it runs on real time. And in order to check which render engines are you using, you can click this camera icon right here, which is called as render properties, and going on top you can choose which engines you want to use, and default it is chosen as Eevee, I think, so that's not a problem. That's good. If you want to change to cycles, you can do that, which will create a bit more prettier but renders slower. I'm gonna go back to the Eevee, and for renderings you want to set several post effects in order to make it prettier. What I always do is at least increase this render sampling to 128, turn on the ambient occlusions, bloom. Sometimes if you have a lot of reflections, turn on screen space reflections. I don't have a reflection to this box, so I don't really need to turn on these. And go to the shadows. If you have a bunch of CPU available, it might be a good idea to make this higher value to have more crisp shadow edges that you see here. If you have lower samples, you see more blurry image. Since I'm using a high-end Macintosh, I can raise up this value really high to have a pretty shadow image. So I'm just gonna do it like that. Okay, so look, that looks good. If I play it, you can see that the box is dancing with this setup color. Now, you can also go back to the material, and you can also change this shader a bit with your needs. Okay, in order to edit the shader itself, you can change this spreadsheet to a shader editor menu. Going into the shader editor like this, and this is the current material that I'm looking at. If you're not looking at the box material, you can check somewhere around here and you can choose which material to control. There's only one material now, so you only see this box. And this is you can also change the same value here as well. That you can also add another node value in order to control these shaders as shadings. For example, you can use the geometry nodes and use the normal value to control the color. As a result, each face color will change based on its normal value, which is also interesting. More like a Rubik's cube. Right? Well, let's ignore that. What I always like to use is this subsurface, which is pretty rare to be used in real-time renderings, but it's pretty easy to use in Eevee. And if I increase the subsurface, it becomes more like a human skin, which kind of penetrates a light. I think it's a fake surface in this case in the Eevee, but it looks really nice, so I tend to use this one when I do the rendering in Eevee. And let's also change the color to something orange-ish. Looks good. Alright. Now, I think I do like how it looks like right now, so I'm just gonna go with this. And what I want to do now is to set up some lighting for this. So let's go to the layout, show up the render view, and let's set up some parameter first. Let's make the resolutions to 4. Okay, and search radius to be a bit smaller, like that. Like that. Okay, and currently the minimum scale is a bit too small, so let's make it 0.2. Looks good. Max scale to 3. Interesting. Maybe that's too big. 2. Alright. Now Asian height is, I think it's good. So it's time to set some lighting. There is one single light available as a default, and we can move this by type G, move around. We can also click this light icon and turn up this power value to make it brighter. But as a lighting theory, it is always a good idea to have at least 3 lighting to make a realistic lighting. So one goes front, one goes on the side, and one goes on the back side. Okay, so let's say this light is the one that is facing front. Okay, and let's make another light by duplicating it. Make this comes to on the side. It already looks prettier. And let's create another light which goes to the back. G plus Z, so that we can move only to the Z direction. A little bit lower for the back side so that we can see some reflections. Okay, looking nice. This can go lower as well. This can go a bit farther, and for the front light, let's make this a bit brighter. And for the back side, we can also change the color of this light, like a bit bluish. You can just try out. And let's make this a bit more brighter on the back side. And for the side light, let's also change this to a bit more warm color, like reddish or yellowish, pink, not sure. Maybe a red. Sounds good. Okay. That looks good. Alright. Now, let's also set the camera in terms where if you want to do the renderings. So click this camera icon here, and you want to move this camera to have the best position. So show up this menu, go to the view and click camera to viewport locked, so that you can control this camera view by navigating the viewport. Okay, somewhere around here looks good, isn't it? Alright, and hide out the gizmos, and also I could go back to the camera. Camera, and I can change between perspective, orthographic. I think I do like the orthographic a lot, so let's change this to orthographic. Now we do need to change the size here. Seems like we cannot navigate. Okay, looks like I do like this view. The reflection looks good. Okay, so that's the final result that I get. Going back to the geometry node and click the cube. And like that. So this is the final project that I have created for this tutorial. Well, I have explained what I have explained is how I often research throughout the website and come up with the logic using this tool. Then how you achieve what you want to create using a bunch of available nodes in Blender. Then finally visualize the geometry using the Eevee. That's the workflow. But often, most of the times when you do it for the first time, I think it fails a lot because you don't know what kind of nodes available in Blender. Sometimes you imagine it's available, it's not really available in Blender yet. Even some essential one is missing still. But I think that's going to change in the future, because this function is official stuff. So officially it's going to be updated. Even in 3.1 there are some new stuff coming out, which is pretty exciting to know. So can't wait for that. But honestly speaking, compared to other geometry related procedural system like Houdini, it is still pretty limited, even if you can compare with a third-party plugin in Blender, which is called as Spellchuck, which is a third-party plugin to create a procedural model. This geometry nodes, the official procedural geometry nodes, is pretty limited in terms of what it can do with the fewer number of nodes. But since this is official, I think it's going to grow just grow up in meantime. And what I really like about this is the connection between the shader is really smooth, so that you can easily interact with the Eevee shader system, which I really like about it, which I really like about this. So without Eevee I wouldn't use it, honestly, because Houdini is much powerful in terms of the procedural generations, but because it has Eevee as real-time renders, that's what makes me use this tool. Because you can easily create this kind of pretty image pretty fast. So that's my thought on Geometry Noes. I would like to post more tutorials on Geometry Noes, but maybe from next time I'm gonna make it a bit faster, because this tutorial was more of a getting started. But from next time I'm going to assume that people knows a little bit of Geometry Noes and right on to creating some specific topic. Okay. That's my plan. Okay, so thank you for watching, and hopefully you like the video. I think it becomes a bit long with this getting started video, but hopefully you get something out of this. If you like the video, please like and subscribe to the channel. And I'm also doing the Patreon page myself. You can go to the page from the link in the description. And I will appreciate if you could support me creating these tutorials for further development. Okay, so that's that. Thank you very much, and see you